In this tutorial, we're going to analyze the motion of an oscillating spring. So imagine that we have a massless spring hanging from a ceiling like so, and its equilibrium length, with no weight attached at the end, is 28 centimeters. Massless in this context just means that the spring does not stretch as a result of its own weight. If, however, we attach an external mass of 5 kilograms to the end of the spring, then of course it will stretch out, and in this case, it reaches a total length of 42 centimeters. Let's define the positive y direction to point upward. In that case, we would say that the displacement of the spring as a result of attaching this 5 kilogram mass was negative 14 centimeters, right? And that's just for the case of attaching 5 kilograms. If we had attached more mass, you can imagine the displacement would have been a larger negative number. If we had attached less mass, then it would be a smaller negative number. But right now, it's perfectly happy to be a length of 42 centimeters, supporting only the 5 kilogram mass. But what if we exert another force on this mass? Let's say that we reach up and pull down on the mass while it's attached to the spring. Well, we can temporarily achieve a new equilibrium. It's a combination of our exerted force downward and the weight of the 5 kilogram mass downward, balanced out by the spring force pointing upward. But if we let go, suddenly that spring force is going to be bigger in magnitude than the weight of the 5 kilogram mass. When that happens, the mass will go up past the equilibrium point and start oscillating back and forth. Let me show you. So we let go, and now the mass is just bouncing up and down with the spring, and it keeps shooting past the equilibrium point, never quite hitting it again. Now you can imagine in a real system, if you wait long enough, eventually friction or something will damp it out, and it will get back to its equilibrium position. To characterize these types of oscillations, we can use 3 different variables that are closely related to one another. They are the angular frequency, the period, and the frequency. Omega is the angular frequency. It's equal to 2 pi divided by the period t, and that's equal to 2 pi times the regular frequency f. We'll calculate all 3 of those variables for this system. But to do so, we also need to know the spring constant of the spring. And to get that, we'll use the equation for the spring force, that the spring force is minus k times delta x. That's how it's usually presented, but of course we can rewrite it in terms of delta y, no problem. The last equation we'll use is the equation for the period of a spring oscillating, and that's just 2 pi times the square root of the mass attached at the end divided by the spring constant. So we'll use all of these equations. Our first step should be to consider force balance on the mass at the end of the spring. When it's just sitting there, and the thing isn't moving back and forth, the net force on that mass must be 0, and that's just caused by a combination of the spring force pushing up and the weight of the mass pushing down. Well, we can substitute in the expression for the spring force that we have over there in terms of delta y. So we do that. Of course, we also know that the weight is just equal to minus mg. That means that k delta y must be equal to minus mg, and we can solve for the spring constant k. So we do that and find that it's minus mg divided by delta y. Now we can plug in numerical values. We know that the mass is 5 kilograms, g is always 9.8 meters per second squared, and delta y we already said was negative 14 centimeters, or 0.14 meters. Calculate all that out, and we get that the spring constant k is 350 newtons per meter. That is the unit of spring constants. Now that's nice because we never have to do this determination again for this spring as long as we don't break it. It will always have a spring constant of 350 newtons per meter for any mass that we attach at the end. Okay? We'll write that down over on the left. Now we can use this to calculate the period of the spring when it is oscillating. So if we do that, we just use the equation for the period of the spring. We know the mass and we know the spring constant that we just calculated, so we plug in those numerical values. We find that the spring's period, oscillating back and forth, is 0.751 seconds, or to 2 significant digits, 0.75 seconds. That means that the spring would go up and come all the way back down every 0.75 seconds. Okay? Next, let's calculate the frequency f. So f is just 1 over the period, and that means it's just 1 over 0.751 seconds. So we can calculate that quickly. It's 1.33 hertz, or to 2 significant figures, 1.3 hertz. Remember, hertz is just inverse seconds. That's the typical unit of frequency. As a last step, we'll calculate the angular frequency. All we have to do is multiply this result by 2 pi. You could also get it by calculating 2 pi divided by the period. Either one of those strategies will give you an omega value of 2 pi divided by 0.751 seconds, which is equal to 8.37 radians per second, or, to 2 significant figures, 8.4 radians per second. Fundamentally, these 3 variables that we often use to describe oscillating systems are so simply related to one another that they are essentially conveying the same information, But different problems will ask you to compute different quantities, and so it's good to know how to get all three.